This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons, and it's Wednesday, October 16th, 2024. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in classical conversations communities. This academic year, our club is working on a lesson a week together as we prepare to answer our children's questions. So Kirsty, I'm excited about today, and I know the semester is drawing close.
It is. It seems like all of a sudden we went from the beginning of the year, and now we're looking at lesson 12, which just leaves us with 3 more after this week in this semester. So we are on lesson 12. We're talking about polygons, and I think one of the reasons that Lee is excited is because this is intended to be a restful week for you. You've heard me allude to the fact that Lee was really intentional about trying to balance weeks that were perhaps a little bit more involved in their concepts with weeks that perhaps feel a little bit more restful. And a lot of that comes from what we're familiar with. And so for a lot of us, we're familiar with polygons because we start at a young age by defining polygons. We don't always start at a young age defining quadratic equations, but just imagine students who start in the math map when they're 4. By the time they get to challenge A, they're going to say, this is all restful because it's become familiar to us. That's an exciting thing to look forward to. So as always, we're going to start by taking a look. We are here on lesson 12. So if you are keeping track in your own math map, whichever domain you are in at home, you want to go ahead and find that domain and remember that you are working through that column. And so that puts us here. The materials that we're using are complex. And so we're in this box here, polygons at the complex level. Now you may notice as we work in 2D that we're going to see those imaginary numbers, those complex numbers perhaps a little less frequently, and especially when we're talking about polygons, because when we talk about polygons, a lot of the times we're talking about things that have measure. And when we measure things, we're always going to be measuring things with real numbers. So we're going to circle back around and we're going to continue to practice those complex numbers. But the imaginary and purely complex numbers may be a little bit less obvious this week. So as we said last week, we have changed from working through National Number Knockout to working through some interesting integers. So this is the number 51. Lee chose this one for us yesterday. So let's go ahead and just take just a couple of minutes. It's still 2 minutes that we're going to spend on this. But what are some things that may make 51 interesting? And so I've put some questions up there that you can think through, some different ways to represent or communicate the number, how you could use geometry, or perhaps if you know an interesting fact about this number.
It's a prime number.
It is not actually a prime number.
You're right, it's not.
That's why I love it so much. It's 2 prime numbers, or 3 times 17 make 51. I feel like 51 is the neglected number. We always use 12 and 36 and 144 and 64, but 51 is just as flexible.
But it does trick us. A lot of us, when you first look at it, it does feel like it should be prime.
It's about AI and programming.
It makes me think of Area 51. I don't know if that's something to talk about.
It feels like it shouldn't be allowed to happen because it's my next birthday.
No, the 50s are wonderful.
So somebody in the chat said 25 times 2 plus 1.
Good.
My first thought was catch up. Mine's 51.
Good.
So just to expand upon it, so 51 being 3 times 17, then the 3 gives me a connection to 24, and the 17 gives me a connection to 34. And that's one of the ways the students who do really well in National Number Knockout become such masters at it, is they get these connections between pairs of factors. So it's another thing that's interesting about it.
How about geometry? What geometric shape could you perhaps use to express this number?
A triangle because of the 3 with
Oh,
17.
okay.
There's 17 of them.
I like that. So perhaps an equilateral triangle that has sides of 17.
That works.
How about a rectangle? How could you use a rectangle to communicate 51?
Well, you could have 5 times 10 and have a one little piece hanging off.
You could. Or we could have one side that was 3 and one side that was 17. Right? So we could use geometry in some different ways. All right, so we've talked about some interesting facts. So if it is the product of prime numbers and not prime itself, does anybody remember what we call that kind of a number? Starts with a C.
Composite?
Yes. Excellent. And here, this is something I discovered in preparation for today that you may not know, but after today, perhaps you'll remember, is that 3 and 17 are actually called Fermat primes. And that's not really the interesting part, but because its factors are Fermat primes, that's the chain of reasoning that lets us know that we could actually construct a 51-gon, a regular 51-gon with basic construction tools. And so we're going to learn more about those construction tools in a couple of weeks when we get to lesson 14. But I thought that was really interesting, the thought that we could use basic construction tools to construct a 51-gon. So
yeah, because it seems like it would be difficult, but it's that 3 and 17 allows us to break it down.
mm-hmm.
So are you saying Vermont?
Fermat, yes, like Pierre Fermat, F-E-R-M-A-T.
No, it's coming out as Vermont, Kirsty, in the scripting.
Fermat, F-E-R-M-A-T, sorry. And basically a Fermat prime is a prime that can be expressed as a power of 2 plus 1. So 3 is the first power of 2 plus 1. 17 is the fourth power of 2 plus 1. So not every prime is a Fermat prime, but 3 and 17 are, which is somewhat interesting, which makes 51 interesting, and then says we can construct that 51-gon. So if anybody does that, send us a picture because I will be really impressed. Might be a great Christmas challenge to give your kids.
But Kirsty, if I don't get a grade for it, I don't want to do it.
Ah, yes. Well, we'll talk about assessment in lesson 15 because grades are not what should be driving us. So let's go ahead and spend a few minutes taking a look here at our cover, our exordium. I'm going to click our timer here. And what would you like to share this week? What do you see either in the art or our quotation or our reflection?
The quotation is from Mary Shelley. And is that the same author of Frankenstein?
It is, yes.
That's cool. Like you think of math and science, and she wrote a very unique science experiment book.
She did.
I see polygons in the snowflake. Hexagons for sure. I liked your word 51agon because I was thinking that when you were asking for geometric shapes, and I kind of I made that term up in my head, and then you said it, and that was very exciting for me.
Oh, good.
Well, I like the quote that's by Edgar A. Guest, but because I love a different poem of his called Baby Feet that makes me so excited. But anyway, it's really, baby feet are really pretty and really cute. And I actually really love the visual of the polygon. There's something beautiful about the symmetry of it and actually even the color choice. I really love that. The polygon art, I should say, the snowflake. Beautiful.
Tanya, you probably should love snow because you probably get lots of it. We don't get too much here in North Carolina.
It's true. We get a lot, and it's coming soon to a neighborhood near you now that Thanksgiving is over for us. So
This looks symmetrical.
How many remember the experiment we do where I'm trying to remember, we did it in foundations and then where we actually grew some crystals, right? And how they grow and helping our students to see that. And so a snowflake is a specific crystal that's grown, right? It's an ice crystal. So there's a way that we can help connect things for our students, right? That when we think of polygons and then extending these ideas, right, to saying, oh, well, this is a crystal. Do you remember doing that? So that's one of the things that we want to remember as classicalists is we really have this opportunity to integrate our learning where traditional education, obviously, but traditional math education, I think was a lot harder to integrate in. And that's why when we think of our topic wheel, math was sort of its own little thing so often, because your books weren't designed to be integrative, right? They were you did math, and we've been told, hey, this is your chance for independence. So stick your kid in front of a computer screen. They don't need to integrate this into everything else that they're doing. It can be separate. And so one of the things that we're really saying when the math map is, no, pull this back in to everything else and integrate this into what you're doing. Math is fundamental to all of it, right? And the ideas that we're exploring are fundamental to everything. And so it needs to be integrated in just like every other strand. It's not its own thing over there. And so there's one way that you could take this study of polygons and looking at these snowflakes and remember that experiment if your children did that in foundations.
another thing,
So
if
I
I'm
want to
looking
add
at
a
seeing
little,
that, oh, sorry, go ahead.
that's okay. I want to add a little side note here because Edward A. Guest was apparently frequent visitor to where I live at Pinehurst. And every year or so, my husband wins a golf tournament. And the trophy is a poem from Edward A. Guest about golf. And I just went online to confirm that that was right because it's hanging in my bathroom, this award that he gets. So that's a little bit about my husband because nobody ever gets to meet him.
That's so cool. I love the integration there. That's awesome. I was thinking about seeing the unseen and looking at the infinite nature of snowflake formation and how there are infinite possibilities about that crystal formation and probably infinite possibilities of polygons too, on the larger end closer to infinity rather than the smaller end because we know we need at least three sides. But in terms of looking at God, it's like the infinite capacities that he embodies and just all the different images of himself that he dabbled into each little soul that he created in this world. And there's something beautiful in each person that can show a little bit of his character. I don't know. That was what stood out.
That's great.
Two
The art reminds
snowflakes are
me
the
of,
same
oh,
too.
sorry.
Sorry, no two snowflakes are the same just because the way that they're made. So you'll never have two snowflakes that are exactly the same.
The art reminds me right along those lines. There's a photographer from the late 1800s named Wilson Bentley who was homeschooled and developed a love for nature and photography, and he used a microscope and a camera to take pictures of individual snowflakes.
It's amazing, isn't it, that when we look at a snowflake, just all the things that we've just said, and we look at this snowflake, obviously magnified, and it's amazing and it's beautiful. And yet, most of us, when it snows, right, you don't see that. It gets lost, right? This beauty that's in these snowflakes, we don't normally see it. Um, but God still cares enough to make snowflakes beautiful. And the Bible tells us so clearly, right? If he cares this much about the sparrow, imagine how much he cares about you. Well, snowflakes aren't even alive, and yet he cares this much about a snowflake, and how much more he cares about us, right? If it matters to have the snowflakes be individual and valuable of their own right, how much more does that matter about us being individuals and valuable in our own right? So, all right. Well, we're out of time. Beautiful conversation today. Thank you for sharing that with us. So let's go ahead and we're going to look at our I squared page. And this page is here because when we talk about polygons, as I mentioned, a lot of the times we're thinking about things that we're going to measure. So not every measurement on here is a linear measure or an aerial measure, the kinds of measures we're going to talk about today. But this was a good place to talk about all of these different kinds of measures. So let's take a minute and why don't you share with us what do the things that you know when it comes to measurement in units?
I know the foundation's memory work about the linear equivalents and the metric measurements.
Good.
So I'm pretty familiar with the length units and the temperature units and most of those time units.
And the prefixes.
Good. So there's a lot on here that we're maybe familiar with. Let's talk a little bit about authority this week, because that's one of the common topics that maybe we don't always get to when we're talking about our I squared invention page. What does this page tell us about authority? Or what do you know about authority when it comes to measurements?
There has to be a standard.
And God hates it when we cheat on these.
Yeah.
And there's consistency no matter where you are for
Good.
each of the different measurements.
Yeah, these are universals. In other words, every language has these same values that are the unit name may be slightly different.
I know that we started with the imperial, metric measure or the imperial system with measuring some king's foot. After that.
I think it's awesome that there is an authority that is correct. But what we use to measure, like if the tool we're using isn't labeled correctly or is off by a little, then we think we're right, but we're not. But it's us that's wrong with the tool we're using, not the actual law or the actual definition of those measurements.
It's a great point, Jill, isn't it? Whenever you use like one of those expanding tape measures, for example, right, and it's got that little piece at the end that'll hold it in place, but over time, that little piece might get loose and move. And so if you really want an accurate measurement, it's usually not a good idea to trust that as your 0 point, because that first inch or first foot may be off by a little bit.
That reminds me of like navigation when we're off by a little bit at the beginning. It doesn't seem like very much, but if you go, a distance out from that, a measurement out from that, it becomes like way off your target point. So accuracy really matters. It's like God's law too. Sorry, going back to that, but God's law is like his is the standard. It's that line. And when we're judging ourselves against our interpretation or instead of what he meant by it, then we can be completely off of the straight path too.
I love that, Tanya, because sometimes we hear paraphrases of Bible verses, or people be like, oh, well, this is a proverb. And they get it just a little bit wrong. And if we're using that as our measure, we could be way off. And so it's so important to always come back to what's God's standard, and making sure that we're using the right tool to measure things.
Something
And
that
then
I think is
gets
interesting.
more,
Oh, go ahead, Jill.
it gets more off as it's repeated. Just like if you have a template that was accurate, but you use that template to measure and cut, and then you use the second one to measure and cut, and you use the next one to measure and cut, it will get worse. And if we repeat our opinion on what God says, instead of everybody going back to scripture and seeing it for ourselves, it gets a little more off every time too, or anything. It doesn't have to only be God's word.
Yeah, and something just I want to be clear on. So it's at the top, you see it's standard international units, and that is the SI actuals logo for these international units. And not a one of them is the consensus of man. Every single one of these units behind them are measured by the speed, which is the time and space of some kind of atom. So the atomic structure is is where all these units come from, except for, like our one friend pointed out, the foot, yard, and mile. The English standards are not, but they're from a human being. So that's just something that I'd have an older student research how these are measured by atomic speeds. I shouldn't say measured, defined by.
Yeah, I think this page is a deceptively simple page, and there's a great example of something being restful because it's familiar to us. But gosh, there's a lot here that we can talk about and discuss, but not today. So we'll have to look forward to that on our next round through the math map, talking about this a little bit more deeply. So let's go ahead and look at our I cubed page or I3 page, which is our Memoria and arrangement page. And what's your initial reaction to this page?
Yay, I know shapes.
Yes, shape seems simple.
Great. So it is. So we initially go, wow, there's things on here that I recognize and this looks familiar to us. It could, for some of your students, also look overwhelming because there's a lot on here. And so this is a great opportunity to talk about, all right, how do I, again, we do this every week, but specifically, I think with this week saying, okay, let's look at this and let's cover up some things and let's find some columns that we're comfortable with. And maybe if we look at the left couple of columns, we're most comfortable there because those are the things that are familiar. Then we might say, let's look at the right-hand side. Are there some things that are repeated on the right-hand side? Or some things that follow a pattern?
The exterior angles are all 360 degrees.
Great.
And it's area equals 1/2 something times something, but base times height, and then I see A times P at the bottom. Oh, except for the square.
Well, it's still something times something.
So when we're talking about area, how many things are being multiplied? How many factors do I have in general, like letter wise?
Two.
Right? That's a great thing for our students to recognize because I'm multiplying two things together for area. What about perimeter? Am I multiplying in general?
Adding.
I'm adding, right? I could describe my perimeters all as an adding, where my multiplication is or my area is a multiplication. So there's some patterns that we could notice just by looking at this. Are there things on here that students who have come from foundations may have memorized?
The area of the triangle, the area of the square.
Good.
Those bottom images look like the spirograph or the whatever, what's it called? Is that a spirograph where you like have this pen and it goes in circles?
Or maybe like stained glass windows that you see in cathedrals or something.
So if we look at those and then we look up at the top, what is it that have been drawn in there to create those images? What's the title of that?
Diagonals.
The diagonals, right? So we may not know at this point, this is our first time through, we may not know what a diagonal is by definition, but that we see these images here that might help us to determine what a diagonal is, right? And to recognize that we're going to have a lot more diagonals as we have more sides. Let's go ahead.
Wait, last question. So based on what you said earlier, would a 51 gon fit on this? Would it be regular?
Yeah.
Okay.
If it's regular, right? So
Sure.
there's another term we haven't defined yet, but we will in the lesson. But a regular polygon has all equal angles and all equal sides. Only in a triangle are those guaranteed to go together. So if I have an equilateral triangle, it will also be equiangular. And if I have an equiangular triangle, it will also be equilateral. And we call that our regular, right, polygon. Notice with our quadrilaterals that my rectangle is equiangular, my rhombus is equilateral, but my square is where it's both. And so once I get past a triangle, I might have all equal angles or I might have all equal sides. They don't necessarily imply the other one. But when both of those things are true, that's when it's a regular polygon. And I can have a regular 51 gon, and then it would absolutely fit on this chart. But there's actually, somebody said there's an infinite number of polygons, right? And so there's an infinite number of 51 gons that may have slightly different angle measures and slightly different side lengths, right? So there's an infinite number of 51 gons. So here's a fun place to play with numbers with our kids because there's an infinite number of n-gons, right? I can have a 3-gon all the way up to a Google gon. But then within each of those, there's an infinite variety of those, right? There's an infinite variety of decagons and octagons and quadrilaterals. Now, one interesting thing is that my 51 gon, no matter whether it's regular or not, will actually have 360 degrees be the total for the exterior angle. So even though we're listing that here for under regular polygons, notice that it's true for all the triangles and the quadrilaterals. We're going to find that that's true for all of our n-gons, is that the exterior degrees will add up to 360. So that I think is kind of a neat constant that's true for all of that infinite variety of polygons.
May I ask a question?
Yep.
Just to clarify what you mean by exterior angles versus an interior angle.
Sure. I'm going to draw this. Let me just turn on my pen. So if I'm just going to use a triangle because they're easy. An exterior angle is the angle that if I extend one of my sides and I measure this angle, this is the exterior angle.
Okay.
And you can't see me doing this, but I'm going to try to do it here because this is the easiest way to show your students that this 360 degrees is always true. If I have my pencil, right, I'm just going to draw it like an arrow. Well, if I rotate my arrow now so it lies against this side, and then I move it up here, And then I rotate it so it lies against this side, and then I slide it along till it goes here, and then rotate it. Notice that as I trace each of these angles, so I've traced this angle, and now I've traced this angle and that angle. Notice that my arrow comes back to where it started. And that's going to be true if I had this here. I'm just going to extend my sides here so you can see what I'm doing. All right, so here's my arrow. I rotate it so it's going here. And then I rotate it so it's going here, here, and I rotate it through that last angle, and I get back to the same orientation. So you can do this with any polygon with your pencil and just trace those angles, and it'll add up those angles as you're doing your pencil all the way around it, and you'll always come back to the same orientation. So it'll go through 360 degrees to get back to its same orientation. And it actually will hold true for concave polygons also, because you'll kind of turn your pencil backwards. So anyway, I just think it's a fun activity with students to help them see that. Does that help answer that question?
Yes, thank you so much.
All right. So let's go ahead and take a quick look at our charts. As we're looking at the charts, I just wanted to, this question came up. I can't remember where it was, but Lee and I were talking about it the other day. We have, and it's a little bit hidden because we've really made it something that's there for tutors, but we're going to make it available where it's also available for parents, but it's on the tutor page. So in the companion, if you're in one of the booklets and you click on the little hamburger menu, and you'll see down at the bottom, there's a link to the glossary, and there's also a link for tutors. If you click on that link, it takes you to the page where there are resources specific to the tutors, and you have to be a licensed director in order to access those resources. But also on that page is a little bit of information about what's the really big idea for this week. And so if you're a parent and you're going, well, what is it? What does it really all matter? It is there. Anybody can access that page, Leslie. You just can't click on any of the buttons, but the content you'll be able to scroll through and read. And so this week, the two big ideas, right? If all you finish this week, if that's it, you get to the end of this week and you're like, man, all I learned was what a polygon was, and that these triangle things are like everywhere. Like that would be a win in my book, especially for your first time through the math map, because that's what this week is about, is polygons. And then as we start to study polygons, we see that all of these different characteristics of polygons are usually defined by how many triangles fit inside the polygon. So these triangles become this foundational shape, and they're foundational in real life as well as in mathematics. But those are your two big ideas. So I just wanted to share that with you as you're looking at these charts and you think, what is it that I have to know this year? That might help you as parents to perhaps rest a little bit more and, oh, okay, well, we got that. And next year, we're going to add some layers to that. I see that there's a question back on the iCubed page, so I'm going to click back. There we go. And can somebody let me know what the question was? I just lost the chat.
I wanted to know, Kirsty, what the numbers are in the upper left-hand corners of the triangles and diagonals column.
Let me.
It means one triangle with 0 diagonals.
Oh, okay.
So a trapezoid's 2 triangles with 2 diagonals.
Oh. Okay, that makes sense. I was thinking segments, but then I got over to the diagonal side and I went, wait, that can't be 20 segments down at an octagon.
Yeah,
so
that's
you.
20 diagonals. So, and you can think of that as a diagonal from one vertex will create 6 triangles. But if I was to draw all of my diagonals from every vertex, there would be 20.
Okay, thank you.
You're welcome. And then if we look at our charts, you're going to see actually that there are formulas for that. So down here in this section right here, where we have some characteristics, where we say they're calculable properties of any polygon and then of regular polygons. These are things that are going to be true for any polygon. And so we've given you on that I cubed page, there are some specific examples, but it's going to be true for any of our polygons.
Yeah, so Michelle, if you look closely, what Chrissy just highlighted there, it's the same title head as the frame. So that once again shows people what the frames are trying to do is where there's data that we could expand upon. It can be in the frame, but the chart has the rules and the titles, the basic formulas.
Great, thanks. I try to make those connections, so that's fantastic. Thank you.
So you guys did a great job of seeing some familiar things on our I squared page. So let's look here because a lot of this hopefully does feel familiar to us, right? It may not feel familiar to our students. So that's a good reminder that we've been through this before as adults, that this is probably material we've seen before, regardless of how much detail we remember, we're somewhat familiar, and that's why it feels restful. For our students, it may all be new. So let's take a look at this and see if you can come up with what is something that is unfamiliar to you or something that you would like to learn more about.
I never knew there was a formula for diagonals in a polygon.
Great.
Piggybacking off of that, looking at that formula for diagonals, I was helping my son when he was going through his high school Saxon math years ago. And for some reason, I don't know, this right here is clicking in a better way than the Saxon did. And I'm like, oh, this is restful and easy, and I understand this better now. And I don't know if it's because it's the second or third time I'm seeing this, or if it's just truly presented in a better manner. And I'm thinking it's the latter. And I'm just so thankful for the math map and what I'm learning as the parent and the teacher.
That is so kind of you. Thank you. It has, it's probably both, right? You're smarter than you were a year ago. We're all smarter than we were yesterday. And then also Kirsty and I and Sherry and Jill and Pabs and the whole team have worked really hard to say, what do homeschool parents need? So we've got a lot of experience there in helping the layout. So I want to say one thing I struggle with still is apothem. And I appreciate when I go through week 12 and correct the problems. The apothem is one that I'll spend time struggling with because it is totally not familiar to me.
Piggybacking off of that, somebody said, right, there was this A and P were two of the variables we use for the area of a regular polygon. A is the apothem, so that word that Lee just said she's struggling with, right? So that's the apothem. And P is the perimeter. So if you were wondering what those letters stood for, that's what they stand for.
That's one of the questions that people, keep asking is, as a parent, how much of it's grammar and how much of it is something I should be able to explain? And so, because I'm used to this, I'm willing to say, okay, I can draw that apothem. I can spell it. I can even put it in a formula. But if someone gives me a polygon and asks me to find a missing number, my brain doesn't go to, oh, what's the apothem formula? It does go to, what's the area formula? Or how does a triangle work, but not to there. So I'm not dialectic at all with the apothem, but I'm okay with that because I know there's always interesting questions to come up with. So I just want to keep reassuring you guys that Kirsty and I really are like all of you. There's things we know and there's things we don't know. And I think it's our years of experience of going, we could fail math tomorrow at some course and go, it's okay, because we know that it doesn't end when the course ends. This is a lifetime of learning. So I just wanted to let you know that even when they're hard sections and you don't know things, people just keep asking me, how am I supposed to rest when I don't know what I don't know? Like, I don't know how to help you, but except to share that we have the same problem.
All right, well, let's go ahead, and because we are modeling what is done in the challenge community day, we're going to pause for a moment and see if anybody has any questions or testimonies from working through week 11 curved lines. Well, that's great. That means you guys are all on board and just raring to go. But hopefully what that means is that you were able to rest in really the grammar exercises that go along with complex ideas, and that we're diving in and putting in the effort to become familiar with the grammar so that that understanding can grow. A lot of us want to skip that. And I was just thinking about scripture. A lot of the times I just want to know, well, what did God mean? I don't actually want to spend the time memorizing because it's hard work. It's not exciting. It doesn't always make me go, oh, wow, right? I'm memorizing. I'm repeating the same thing over and over again. But it's becoming familiar. And as I memorize it, that then I'm able to make connections and go, oh, wait a minute. Now I see where God said something in the Old Testament and the New Testament. And he's saying the same thing in multiple places. And that only happens if I've invested that time in becoming familiar. It only happens when I've memorized verses, right? So for example, we're doing a study of the Psalms, and we were reading Psalm 22, and it opens up with, my God, why have you forsaken me? Right? Well, if I wasn't familiar with the story of the cross, I wouldn't recognize that those are the words that Jesus used when he hung on the cross, right? And we see that David cries out in the Old Testament, and Christ cries out in the New Testament. And then the whole psalm, although it's prophetic, it was also written for one man to express his struggle. And oh, guess what? The ideas that are in that psalm can express my struggle too. But I see this beauty and I make these connections because I've memorized or at least become familiar with different parts of scripture. And so I just want to encourage all of us that sometimes when we're working through the math map, the glamorous part of math doesn't necessarily lie in the grammar. And yet it's the investing the effort and the time into the repetition, into the memorization, into the grammar that's going to let us make those breakthroughs later on. So just I'm encouraging myself as much as all of you that have how important that is.
Can I just say something real quick, Kirsty?
Please.
So you were generous enough to give your time to those of us that are directors with your office hours, and you and Bab spent time with me in with regards to lesson 9, and yesterday was my lesson 9 in community, and that wrestling allowed me to be more comfortable with my students who literally just I've got one student that's very advanced, but the kinds of grammar that we were going over, she didn't know that grammar. And it was a win for her. It was a win for me because I could communicate. And then I have another student that he says to me, it's all confusing. It's all confusing. And there was a breakthrough moment with him too. So I I loved hearing you say that because it's true, and I just experienced it yesterday. So thank you.
Well, thank you for sharing. All right, so let's go ahead and take a look at a couple of our page tops here. And this is a good reminder that, right, we have these great lofty conversations and they matter, right? That it really matters to give our students the time and the space to have conversations about math and about the grammar. But it is a math curriculum. And so there's value too in calculating. And so we're going to see here that as we look at our different shapes, we have the opportunity to calculate and practice. So let's go ahead and it says here first to label the shape. Now, I like to oftentimes go across and just focus on labeling. Some people might prefer to say, I'm going to label the shape, calculate the area and the perimeter, and work vertically. And there's no right answer. So if you don't like the way that I work through this, you can work through this the way that you like to. I just know that for my brain, if I'm in a labeling mode, I just want to go ahead and label each thing. So I have a triangle. In my next shape, I see some hints here. And your students may at this point know what these shapes are, or they may not know what these shapes are. But you can look, this is, although it's on page 1, all the quadrilateral information is going to be on chart 3. So I just wanted to point that out in case you need to look at that. So as we look here, anybody want to tell me what shapes are those that we're going to be looking at?
The first one is a rectangle because there is a longer side on one side versus the height. I guess the base is longer than the height.
And how about our next one?
You could also call that a rectangle.
You could. Does it have a more specific name?
It does. Square.
Square. Good. But that's a perfect, right? Those are some great conversations to have with your students. I really wanted to stop and say, right, that stopping and saying, oh gosh, a rectangle, well, it could be a quadrilateral, right? A square could be a rectangle, it could be a rhombus, it could be a quadrilateral. That those are good conversations to have. Now we might want to say what hints here help you, right? So with my rectangle, knowing that there's a right angle, that might be a good hint that it's a rectangle. And when I look at the square, maybe I look and I see that my area formula is side squared. And so that's my hint that it's a square. So it's okay to use all of those things. You don't have to work linearly. You can look at all of that information to help you figure that out.
I like that you're using, oh, sorry. I was just going to say, I like that you're using base and height for the rectangle also because, you know, we use length and width and base and height and altitude. Like there's all these different words. Some of them are synonymous and some are just, you know, sometimes overlap and sometimes don't. So I noticed that you had equals length times width equals base times height on the iCube page, I think. I really like that.
Good.
Yeah, the square could have been B equals 9 meters and B squared.
Right.
And that's the thing that's hard is for kids, or for, it's hard for teaching math is there's so many synonyms.
Right.
So then we're asked to calculate the area and the perimeter, and we're given for our triangle, right? We're seeing here that even though we have lots of information, everything is labeled, right? We've told that B is 6 meters, H is 4 meters, and so I can substitute in. So these are great substitution exercises. So my 6 and my 4 would be 24 times 1/2 would give me my 12 meters squared. We didn't put the meter and the meter in just because of limitations of space. But I will tell you that here is a clear example of the difference between Lee and I. I come from the math side, and I think that unless I really need to have a unit, just use a number. Lee comes from an engineering side, and she is firmly committed to giving you units. So we often have that conversation. But it's been good for both of us because it really makes us work to be clear in what we're communicating. So just so you know, sometimes you'll see that we are giving units. We sometimes have to leave them out just for space, but we always want to be encouraging our students to be paying attention to that. So for perimeter, even though we're substituting in 5, 6, and 5, we're really substituting in 5 meters, 6 meters, and 5 meters. So my answer would be 16 meters. And the reason why we want to stress this or emphasize this with our students is to help our students remember that square units go with area. And there's my invisible 1. My linear units go with my perimeter. So I'm not going to work through that for all of these because I think that you guys probably have that. Let's take a look at our next page. And we're not going to do this whole page, but I wanted to share this with you because I think this is a really great example of working through an analysis of a shape. And you're going to see, especially as we look at other domains, that here we have sort of a triangle, and we're going to say, what are all the things that we could talk about with this triangle, right? So as we look at the triangle, we could name all of its vertices. All right, so here's my other letter, so TRI. And then notice we say there's 3. We're asking for 3 names of the triangle. There's actually more than that. But this is a great opportunity to remind our students that we can start with any letter and go in either direction, right? So I could have triangle TRI, RIT, or ITR, and then I can also go the reverse of those. So we're giving them the opportunity to practice. For the person who asked about the exterior angle, here's a great opportunity to see where we're actually naming that for you to clarify, right? So RIE or EIR, whether I go from R to I to E or E to I to R, I'm tracing the same angle. And so that helps me to identify what my exterior angle is. Looking at this with sides of 4, 5, and 6, right? Is that an equilateral, an isosceles, or a scalene triangle?
Scalene.
Great. And is there any indication that it's right or obtuse, or do you think we have an acute triangle here?
I think you have an acute.
We have an acute triangle. Now, we could use the Pythagorean theorem to confirm that. And so for our older students, that may be an additional step that they would see. But here we're looking at this and we're figuring out that it's an acute triangle, mostly based off of what we see. And then again, we could look at its perimeter and its area. And this is a great example of looking at a shape in the non-coordinate plane. There's a lot of analysis that's easiest when we don't have to worry about the location, right, of a point, where we can just say, this is how long the sides are. If we were to take this exact same triangle and put it in the coordinate plane and have to pick coordinates that gave us exactly the side lengths of 4, 5, and 6, we would get what we think of as ugly numbers, right? They wouldn't be nice natural numbers. They would be probably they could even be irrational numbers, right? So this is a great example of where a lot of the times when we're dealing with polygons, a lot of the analysis is going to be easier or more straightforward if we're not in the coordinate plane. However, we look side by side and we see that we can look at triangles in the coordinate plane, and we can calculate things based off of location. And so this is how we're going to be able to see several examples of looking at triangles, or looking at all of their characteristics, both from a coordinate and a non-coordinate plane, to help students to really get to the point where they go, well, here's all the things I know about a triangle. So one of my favorite lesson pages. Just wanted to share that. So don't forget, every week we want to remind our students of what their tools are, that we can use those solutions for working backwards, that we do have the opportunity to extend our conversation through some of those activities on the inside back cover. We've got the game and so forth. And of course, you have resources too. Next week, we'll be talking about circles and ellipses. And I just wanted to point out, I think we go through lesson 17. We're going to finish up lesson 17 before we break, but we will continue to meet afterwards. So after Thanksgiving and during December, we'll continue to meet so that if you have questions that come up, we'll be here to answer those for you, but we're going to pause working through the lessons until after New Year's so that we don't get so far ahead of families and what you're doing at home.
Hey, I want to add, just go back to that for a second, Kirsty. A lot of parents who haven't had the training or been on the book club are at a point now they're going, wait, where is my help? And so maybe we can do a screenshot of this next week, Kirsty. And then this is something you would help us if you could print this off and just keep it in your car or give it to your director to hand out to the parents, because not everybody's been as diligent as you guys have been in trying to discover where all the resources are. But we want to help everybody we can. We don't want them to think we're not around to help.
Yeah, we talked about that yesterday. Lee, Sherry, and I had a conversation yesterday about the thing that Classical Conversations does really well is helping you find friends to help you, right? That we can't be in everybody's homes. But you don't need us in everybody's homes, right? That when you have a friend who's working through something, when you work together, you're going to make progress. And so through the book club, we get to be your friends and you get to be our friends and we're working together. But our hope and our goal and our prayer is that each of you is now going to turn around and be a friend to somebody else and help them. And so pretty soon, if we're all seeking somebody else to befriend and be a mathematical friend to, then everybody can have a friend and feel equipped walking forward.
Like that, mathematical friend.
And so that brings us to our time where we are going to answer questions. I'm going to stop sharing this and I'm going to go to a different whiteboard so that I have to remember every different program is a little bit different. So let me just get back so I can share this screen. I apologize for losing you all. All right, share this screen. All right. For some reason, I don't get all those jagged lines when I'm on this whiteboard. So what questions do you guys have?
I just have a quick one about the errata pages, because right now there's so much support and so many places to look when we're looking for help with the math map. And the errata page I know is on the bookstore website. Is there ever going to be a time in the future where maybe that gets added as its own thing in the hamburger menu on the companion at all to kind of give us one less place to hunt down help?
So right now, it is in the companion. Babs or Shauna, well, I think Babs is on the call. She may be able to tell you exactly where in the companion the link to that is. We can look at making it so that it opens up within the companion. Right now, it just links to that bookstore website because it's a separate process that errata gets updated on the bookstore website through one process. So we're just linking to that so that we have the most common or up-to-date information. But we can certainly look at getting a copy of that document and having it open up within the ecosystem of the companion. So Babs, if you can make a note to remind us to look at how to do that, we can do that if that would be easier.
I appreciate that. I think that little hamburger menu is probably my favorite part of the companion because I can click on it and see a list and, oh, my glossary is right there. My page is right there. My tutor help is right there. if that errata was right there too, that would be really helpful, at least for me.
Well, great. Well, no, that's great feedback, and we'll look at including that in an update.
Thank you so much.
I have a question from booklet 7, which is where we were our last community. Page 4. And I tried to find information myself and just couldn't find any explanation for this. And it's not in that top box where you have all those helpful videos. So page 4, the note the common base of X and A and simplify, I just couldn't figure out the pattern from the left column to the right column of like how
Sure.
we're plugging in numbers.
Okay, so this formula, log base A of X is the log base B of X over the log base B of A. So the exercises here are going to allow you to change the base of a logarithm, and we're going to be using powers that we're familiar with. But I also want to let you know that perhaps the most powerful way this gets used is that it allows you to be able to use your calculator to calculate any logarithm. Because if you had something, for example, like log base 7 of 43, right? Or let's even say 0.51, right? There's no way that I know any powers that are going to help me with this. But there is some power of 7 that's going to at least get close to 43.51. And so what this formula lets me do is rewrite this either as log base 10 or as log base E. And so here, my X is my power, so that's what's going to be on the top, 43.51. And my original base is going on the bottom. And the reason why I chose 10 and E is because on your calculator, this is just log. So I would have log 43.51 over log 7. That's my common log. That's what my calculator is. Or log base E is my natural log. And so that's another calculator button. So those are both calculator buttons. And that is what's going to let me use my calculator to calculate these logs that are not nice even powers that we know. Let me just draw a line here. So that is the eventual application of this formula. But what we're looking at here is recognizing that if I had something like log base 9 of 81, it's not asking for a common factor, but it's asking for a common base. And so we see here, we're told that we can use the common base of 3. And so all I'm doing is I'm putting things in place, right? So my A and my X is on the top, my A is on the bottom once I know what that common base is. And what that means is that both 81 and 9 are powers of 3. When we say that it's a common base, what we're saying is that 81 and 9 are both powers of 3. And that's because the fourth power of 3 is 81, and the second power of 3 is 9. And so now I can rewrite this as 4 over 2, which is 2. And so what we're doing in these exercises is really just practicing rewriting these things in these different ways. So you'll see there that we're given the common base in each of these. So if we look at the log base 25 of 125, this is a great example here of where if I said 25 squared, I get 625. So this one can't be simplified easily. But I can recognize that 5 squared is 25 and 5 cubed is 125. And so this is where 5 is my common base. And so that's where I now choose log base 5. And my powers go on the top. My index, my original base goes here. And now I can see that this is 3 and this is 2. And so what I'm saying is that the 3/2 power of 25 is 125.
I
And
don't
so
have
if
the
we
lesson
look,
in front of me. That 25 to the 3/2 isn't in that problem set, if I'm remembering right. You're just showing us how it works. Or did I miss it? Am I forgetting?
no, it should be. That's
it's
one of the problems from that problem set. But it's never written as 25 to the 3/2 power of
That's what I'm
25.
saying. It's
Yeah,
only written as the equation. Okay.
right. I'm just showing, I just wanted you to see what this means when we get there. Yeah, this is not part of the answer. That's just extra information. And so if we look at the one underneath that, where we say the log base 64 of 32, right? Again, we're not, there's not a common power of 64 that helps us to see 32. But if we're becoming familiar with our powers, we may see that the 5th power of 2 is 32 and the 6th power of 2 is 64. So this 2 is my common base now. So when I have my common base, right, and my 32 is on the top, my 64 is on the bottom. And so that's where I end up with 5/6. And what that means is the 5/6 power of 64 is 32.
Okay, thank you.
You're welcome. And it's
Wait, did that help, Kelly? You said thank you, like maybe not.
No, it did. I think it's something I'm going to have to keep chewing on, though. And it was the last one that I got stuck on. Like I was following along, when I do the work myself, not with my student. And it was the last one that I was like, okay, but I can't figure out that last one.
So it's just like you can't divide if you don't know multiplication very well. You can't use logs if you don't got those basic exponents memorized. That's where the struggle is with these.
Yeah.
And I just wanted, this is a great example of where there's one part of one page that's going through this. So if this is the first time that you and your students are encountering this and you're going, man, this, like, we got to this part and we're just really not seeing this, you're welcome to wrestle with it, right? There's nothing, I'm not saying don't wrestle, but you can't wrestle with everything on the pages. So it's okay to say, you know what, we're going to come back to this one. And this is where, if you find it in your chart, it is on the 3rd chart. It talks about the base change formula. That's a great place to get your highlighter out and highlight your chart. And then when it comes time to a break and you're like, okay, I'm going to go back and just look through my charts for some of those things I highlighted that I wanted to revisit, right? You could come back and revisit this again, maybe when you have a break, and say, okay, let's go back and let's go take a look at that base change thing again and see if it makes a little bit more sense now that we've got some distance from it.
You said that's on the 3rd chart?
Yes, it should be on chart 3 at the top. There should be, just looking.
While she's finding that, if you take a break and you go back and do math, wonderful. I'm so proud of you. Hardly anybody does that, but here's how I would use it. I would be looking at, my lessons before the students get to it, and I would look at it and go, oh, this is where I struggled last year. Let me spend a few minutes on that before I introduce it this week to the kids. Because then you don't have to do the whole chart or the whole lesson, just that one thing that you want to know more of.
It is on chart, it's on chart 7.3 at the top where it says simplification processes. And under the what, it says logarithms convert base to base.
Thank you.
Right. Are there any other questions?
I have a question.
Sure.
Looking at 9, lesson 9, page 8, extending the vectors, graphing the vectors. Looking at the chart 4 to kind of help with converting that, it said that to draw the first vector from the origin. And so I was looking at the answer key, and the first vector is not actually drawn from the origin. Is that something that we'll learn later on, or is that?
I believe that that is actually in the errata. So I would, because I happen to have just seen that corrected in the errata recently. So yes. So I think that that's available. If not, if you email the math map at classicalconversations.com, Babs or Shauna will be able to get you that correction. But you're
Okay.
yes.
And then another, maybe it's an obvious answer, but I don't have any frame of reference doing this with my daughter. And so basically, like on the previous page, page 7, whenever we're trying to figure out doing the vertical line test, horizontal line test, is it a function? Does it have an inverse? If it's not a function, will it not have an inverse then?
Correct.
Okay. Awesome.
Yeah,
It's one
it
of those
has to
kind
be a
of
function to have an inverse.
something that might help you is to take those words, relation, function, inverse, in the line test, and almost make a genus species tree. And then rewriting it that way might help you memorize it.
And then one more question. Again from 9, page 15, figuring out whether piecewise graphs are functions or not. How do you figure that one out?
Okay, so say that. So what page are we? Sorry.
No, you're fine. Page 15 from week 9. It's the bottom portion, or I guess the middle portion of page 9.
So once you sketch it, that's where you're going to, once you sketch it, you can use your vertical line test to see if it's a function. And
Don't you mean horizontal?
no, vertical line test for functions, horizontal line test for inverse.
So all of them, though, have a point where if you drew a vertical line, they would pass through both of them. Is there something specific about like the end points or the
Yes,
actual circle points?
I'm just looking so I can say, so yeah, so on that middle one, right, we see that it does go through because the points are closed, and so it does go through that twice, and so it's not a function. But on that last one, here, let me clear this. So on that last one, we're given, this is the function. Y equals 2 if x is less than 0 is less than or equal to x is less than or equal to 1, and 1 if 1 is less than x is less than or equal to 2. So between 0 and 1, inclusive, y is 2. So here's my 2. So that means this point and this point are included. So they're closed circles. But y equals 1 between 1 and 2, but 1 is not included. So that would be an open circle, line, closed circle. And so even though it looks like my vertical line passes through both, because that's an open circle, it's not included. We're showing this is my endpoint, but it's not really included. So this actually is a function. So yes, those endpoints really matter when we're looking at our piecewise functions. Those endpoints really do matter, because if one is closed and the other is open, it's still a function. But if I just did this, let me change my color here. If I just did this, if I said 1 is less than and I colored this in, then it would be not a function. Does that help clarify that?
That makes so much more sense. Thank you.
You're welcome. All right. Any other questions that are waiting? I don't see any hands raised.
So sorry. I have a quick question. Back on booklet 7 on page 14, it says simplify the average of squares. So I understand how to simplify average of squares. And maybe this is a little bit different question, but it says in a series of 4 games, a soccer player played 2-0 or scored 2-0, 3, and 4 goals. So why are we squaring those numbers for his, why are we simplifying average of squares, but we're not really figuring out how many, like his average score? I'm just not sure
It
why we
has
have
nothing to do with soccer. It has nothing to do with soccer.
Okay,
it was just to say, here's some numbers and practice this because we're in lesson 7 and we're doing exponentiation. That's all that is. It has
Thank
nothing
you so
to do.
much. Thank you.
Yeah, I had somebody else ask me, they're like, I don't understand soccer, so I don't really know what this has to do with soccer. And I say, it doesn't have anything to do with soccer.
Okay.
So eventually what will happen, as you go into binomials and on, there'll be some sort of statistical problem where it makes sense. But right now we're just, so you can imagine up through about complex, we're practicing just plain old averages. So I threw a couple of those in complex and monomials just to prepare for more math that's coming in the higher grades.
This is just so fun learning together. You guys, what a great blessing it is. Just so blessed.
Thanks, Tanya. I think that's why Kirsty and I don't give up, because you guys at the book club just makes it all worthwhile.
All right. Any other questions?
I don't have a question, but I did want to let you know that I was just talking to my youngest son, who's in Challenge 3, yesterday, and he was doing some math from the math map, and he said, "Mom, I'm just telling you, not only is this so much easier than the way we used to do it, but it's just better." I said, "So what would you tell people?" He said, "I would just say it's better." So he really didn't elaborate. He just kept repeating, "No, Mom, it's better. It's just better." So anyway, I mean, he's been doing this since Challenge A. We even tried to, pull a little bit of Saxon in just to say, well, we've done the same booklets over and over, but he's growing and he still loves it and he still says it's better.
Is he on complex, Jill, or is he piloting? Are you guys piloting further on?
He does have the monomials pilot books this year, but it's the first time he's had anything other than complex. So he had complex in A, B, 1, and 2.
Wow.
Yeah, I think there's a lot to be said, right? When you hear like Jill's family have gotten their use out of those complex booklets. And just a great reminder for, so for you all are here and asking those questions, but as you're talking with other people, to let them know it's okay not to get everything done, that you don't have to squeeze every little ounce out of complex in the first year, that there are people who have used it for multiple years and continue to be blessed by it. But that we're going to see this incremental move through the domains. You're going to have this opportunity for that same sort of experience to grow and to learn. Well, thanks everybody for another great week. It's always a blessing, as Lee said, to meet together with you, to be encouraged by you, to spend time with our math friends. And so I look forward to seeing you all next week when we talk about circles and ellipses.
Thank you.
Dr. Gilpin, are you still on at this time?
I am.
Would you be willing to look back again with me at booklet 9, page 8 with the vector graphs? I'm still a little mystified as to how those work, even though someone just asked about them and I just still am a little lost.
So page 8, did you say?
Page 8 at the top with the vector graphs. I feel like I see how to, you start at the origin, count along the x-axis and the y-axis, and I feel like I could graph a point in those positions, but I'm not understanding how the vector lines are working.
So let me just clear this. So the images that are there, unfortunately, have been updated. So let me show you what they should look like.
Okay.
So here's your Y and your X. And so R is 3, 2. And so unfortunately it's just drawn in the wrong place. So if this is 1, 2, 3, 1, 2, R should have been drawn here. And then -3, 1 could be still drawn from here. I would go back 3 and up 1. And so there would be my S. And so T would be here, which would be my 0, 3, right? 0. So that R was not drawn in the right place. And then we see the same thing with the other side. Let me change my color here and show you what that one should look like. So U should be -1, 2, which would be, so -1, let me get that, go away. There we go. -1, 2 would be here. That would be my U. And then -3, 1, coming from there, we go back 3 and up 1. And so that's my V. And so my resultant, when I add them together, I go from the origin to the end, and that would be my W, which is -4, 3. Does that help?
For that side it does. What about on the left side for write the vector components? Because for some reason to me it looks like just rays of light bouncing all over the place in mirrors. It looks, I'm so lost on how to do that.
Sure. All right, here we go. So let's look at this one. So on this one, we have vector V, which is -4, 3. So -4 is about here. This is -4. This is 3. This is V. And so my X component is going to be this part here. And so it's going to be my distance along my X coordinate. So V sub X is going to be -4 and then 0 because it's just my horizontal component. My Y component vector is going to be this distance here. So that's going to be nothing, right? Nothing in my horizontal, but 3 in my vertical. And then looking at U is 4, 4. So 4, 4. Here's 4, here's 4. My X component is going to be 4 and then nothing vertically. My Y component is going to be, again, 4 and nothing in my horizontal component. So does that help?
A little bit. I guess I was looking at it. Yeah, I was wondering when I was looking through the solutions to try for help, I was wondering where the numbers were coming from. So that does help because I'm just taking those coordinates from the V or the U and then kind of spelling out which one is the X and which one is the Y.
That's it.
Okay, thank you. That
You're
helps a
welcome.
lot.
Glad we could clarify. And now everybody that got off early will be like, oh, we missed out.
They have to watch the recording.
There you go. I'm leading this on Friday morning, so this will be great. Thank you.
Oh, good.
Thanks, everyone. Bye.